So this is the class number 10 for climate science, and resume with the learning visualization. So we completed the convolution neural networks, which was the fourth course in the series. So today we will see sequence models. Now this is the fifth and the last course of the specialization at Coursera, and it's moderated by taught by NUNG, and these are the sequence of or the table of contents. So why do we need to learn sequence models? Although this course is focused more on natural language processing, but we have time series data sets in our field that that is very important. We Okay, yeah. So we have time series data sets in our in our in our climate science data set in our climate science. So we have a lot of time series data sets, and so this course is primarily oriented towards natural language audio. So audio, you can consider it to be some form of non-linear time series data set, and they also talk about that there is other sequence data, and because so deep learning is leading to state of the art in sequence algorithms. So a couple of days back, not so today is for 6th April. So on 4th April, Google has launched, like they announced that they have built this big model which they are calling it as a pathways language model. So this is a natural language processing model, and it's a state of the art in NLP, and it can perform various tasks like question answering, performing arithmetic, code completion, summarization, language understanding, physics question answers, jokes, translation. And before Palm, GPT-3 was the state of the art, and so you can go ahead and see the details of this model. So it's a 540 billion parameters model. So these are the number of weights that they have used. And although since so I am just showing this to you uh, to give you an idea of what what is the state of the art in sequence models, but these things are directly applicable to our time series problems. Or if somebody wants to actually work in some kind of, or if you want to do a project on in this course on maybe how would you build a disaster management tool. For example, there are flood events, right? So a lot of people will tweet. Okay, so if somebody says, I am stuck here and I need food, and the other person says, oh, I'm stuck here, I'm about to die. So the disaster management authorities, they are limited in their capacity, or they are, if they are limited personnel, so many messages are coming now. How to filter out which one to focus on, and which one to keep for later on. So an NLP system, and um, that is a time when things are time critical. So you do not have time, so you need an automated system which can analyze so much of textual data, and it can tell you, for example, maybe rank the tweets, and it can tell, oh, these are the messages which are top priority and we have to handle. So those kind of climate applications can be built using NLP, which I think people have tried, but still a lot of work can be done. So you can use sequence models in that aspect. Now the first concept in sequence models is recurrent neural networks. So we have seen neural networks in our previous classes. So what are recurrent neural networks? So recurrent by the so you can think of it as some kind of network which are repeating, or which have which have, for example, a single variable, but which has data in the time dimension. So it has got temporal data, and there are various variants of recurrent neural networks which are also famous as RNNs. So the variants are LSTMs, GRUs, and bidirectional RNNs. So first we will discuss about why we should study sequence models. And so the first point is that they have greatly transformed learning on sequences in the past few years. So everything that you do, like every small thing you do, you search on Google, or you use Swiggy, or you use Ola, you use everywhere, there are language models that you are using knowingly or unknowingly in your daily life. So like you should know what is it that's driving these applications. And so there can be some the speech recognition is one of the example. In speech recognition, what you would basically do is you would do a sequence to sequence prediction. So you have an audio, right? You have an audio input X, so which is the wave sequence, and you have a label Y, which is the text sequence. So if, let's say, I'm speaking, and uh, so these days there are even inbuilt caption generators, that if you speak, then it will generate a caption. So that's an example of speech recognition. Then we have another example, which is music generation. So in music generation, it's the type of architecture you would use is 1-2 sequence. So one number. So let's say I just start with a word, and then the model should basically create music out of it, or it should create a sequence of words from it. So that's the music generation task. Then we have the sentiment classification. So if you have a sequence of inputs, so if you have a text sequence, and then Y is, let's say, if you are working on movie recommendation system, or some kind of, even you can apply this to our climate science. Like you can take a lot of papers, you can take PDF of papers, and you can try to find out what is the sentiment of the research community as a whole. What does the community think about my research question? Like, for example, people working on monsoon. So what maybe you can generate a summarizing algorithm, or you can have a controversial question which the community is divided upon, and you can try to build consensus, or to make an understanding of what are the publications, or what are the papers saying about it. So you can generate that kind of a sentiment classification algorithm. Then you have a sequence to sequence, as we have already seen in speech recognition. So in DNA sequence analysis, is also a sequence to sequence problem. Machine translation, that is translating from, for example, one language to the other. That's also a sequence to sequence problem. Then we have video activity recognition. So in video activity recognition, the input is your video frames. So you have, for example, CCTV frames, right? And your label is 0 or 1, for example, theft or robbery. So if you have, let's say, even 10 CCTVs at a location, and theft has taken place, now it's a tedious task to go and see and check each of the videos from all the CCTVs. It's a very time consuming task. Rather, if you have an algorithm through a model through which you can pass the CCTV footage, it can tell you where the robbery took place, and you can go there at that time and see, and get the information about about various about the activity that took place at that location. Now this kind of video activity recognition has been directly used for precipitation nowcasting as a precipitation nowcasting example. So this paper came out in 2015. uh, and yeah, so this is it's already cited by more than 4,800. It's already got more than 4,800 citations. So what they do in this is, so this is also a problem. This is also a sequence learning problem. So they propose this convolutional LSTM, wherein you have a sequence of images, and since it's a sequence of images, so they are using LSTM, and it's a machine learning model for precipitation nowcasting. So if you have a sequence of input maps, so if you have let's see if they have some visualization. So if you have a sequence of input maps, or the precipitation at time t and t plus 1, and you would want to know the precipitation at time t plus 2, t plus 3, t plus 4. So that's an example of a sequential model, wherein this is inspired from the CCTV example that I was sharing with you. So in this model, we'll try to see if there is some good visualization. Yeah, it's something like this. So if you have a sequence of maybe satellite images or some data set, time, for example, this is at time 1, 2, 3, 4, 5, and you want so this is you have to make the architecture of your model. So you can create the label input or the training data set in a way that the input is at time t equal to 1, 2, 3, 4, 5. The output is at 6, 7, 8, 9, 10, or the output is maybe you can say 2, 4, 2, 3, 4, 5, 6. So that 6 is the additional value that you are trying to create out of this model. And this algorithm, so she et al, what they have proposed, convolutional LSTM, this is used as a nowcasting algorithm in many operational as an operational model, I think in Hong Kong or Shanghai. So it is actually used, and it is a pretty successful application. So this video activity recognition is not just limited to the sequence models, or like the typical traditional utilities or the traditional applications. You can also use it for various climate applications. And then comes the example of named entity recognition. So for example, you have an input as a text sequence, and you want to find out what all text or what all words in that text sequence are words or are nouns. So you can create that kind of a label data set. So for example, Harry Potter and Hermione Granger invented a new spell. So in this case, Harry and Potter are names or are proper nouns, and this word "and" is not. So you labeled it as 0, and Hermione, so you label it as 1. Granger is also a proper noun, so you label it as 1. And these words, they are not proper nouns. So that's a very popular application, named entity recognition, like wherein people try to find out the names or the proper nouns within in a sequence of text. So you can build it as an extreme event detection problem, wherein this can be the time series data set of rainfall at a location, and you can label it as 1 or 0 depending upon whether it's an extreme event or not. So you can basically like tune it to your application. And in this case, so we can see that both the input x and the target or the label y, they have a shape 9. So the number of elements are 9, and x superscript 1, so that is represented as so that's the first letter or the first word. X sub superscript 2 is the second word. So here these are the inputs, and the labels are represented by Y. So the notation is Y superscript. So you can see that we are labeling the names as, so wherever it's a proper noun, it's a 1, and tx is a notation for the size of the input sequence, and ty is the notation for the size of output sequence. So in this case, tx and ty are equal. You can have you can build such kind of training data sets where it can be tuned to your application, and so it's equal to 9, although they can be different in the other problems. So x superscript I t is the element t. So for example, Potter is the element 2 of the sequence 1. So xit is element t of the sequence of input vector I. Similarly, YIT means the tth element of the output sequence of the I training example, and TXI is the input sequence for the training example I, and similarly TYI is the length of the output sequence in the training example in the ith training example. So this is the, for example, this can be the second training example. So this entire thing is the ith training example. Now, how to represent words? Like, we are talking about dealing with language, and so this course is on like sequence models and oriented towards NLP, which stands for natural language processing. Now, a challenge is that a word is not a number, right? We How can we do computation on word? So that's what we are going to see in this from this course. And one of the challenges is, so yeah, as we said, how to represent a word. So first is you need to have a vocabulary. So you first is, for example, we are working in the English language, and we need to have a vocabulary which is a list of all the words in that particular language. And so each word will have its unique index with which you can represent it. So you can just list out the words in the you can have a dictionary or a vocabulary, and sort the words in an alphabetical order. So modern vocabulary sizes range from 30,000 to 50,000 to maybe 100,000 also, and some big companies can even use a vocabulary of size up to 1 million. So you would need all the text, and all you would need the most occurring words in the vocabulary, or you can search for online for the most occurring words. So you have to build a vocabulary list, and then what you need to do is you would create a one hot encoding. So this is like the first step towards understanding how you would represent a word as a number or as a vector. So you have built a vocabulary now. Now you have so many words in the vocabulary. Now each word has to be unique, right? So for each word, so you would basically encode it using like, this is just one of the technique. We'll see other techniques also. So you can encode this as a one hot encoding sequence, and so if you meet a word which is not in your dictionary, so you can assume it as, so just like we have nan, when nan, while doing our analysis for numbers which for missing numbers, so you can add a token ank to represent the unknown text. Okay, so what do we mean by when we say that we are trying to create a one hot encoding vector for a word? So for example, we have this sequence: Harry Potter and Hermione Granger invented a new spell. So here x superscript 1 is the word Harry, then x superscript 2 is the word Potter. So for example, Harry is the 4075 word in our vocabulary. Okay, So we will have a one hot encoding in such a way that 4075th element is 1 and all others are 0. And similarly, if Potter is at the is at so we have also, if you remember, we said we sort the vocabulary in an alphabetical order. So this word Potter comes in the as 6830th element. So the vector representing this, so the size of this one hot encoded vector will be equal to the size of the vocabulary. So the total length of this vector is, for example, 10,000, and in the 10,000, in the amongst the 10,000 words, so 4075 is the index, or Harry is occurring at number 4075, Potter is occurring at 6823, and is occurring at 367. So like this, you will basically, first of all, you will encode all your words in the form of one hot encoded vectors. Now the goal of this is to learn a mapping using a sequence model, and to the target output as a supervised learning problem. So now once you build this kind of a system wherein you have transformed your words into vectors, and you already know, right? So if it's a name entity recognition problem, so you have already created these labels, so these are already numbers. So you have already also created this x as so many one hot encoded vectors. So this is your input and this is your now target. So you have to build a model. So these are the different. So you can have 9 different neurons taking these one hot encoded vectors as input, and you have the target as your like in the named entity recognition, you have the labels, the label data that you have created. So we will see now what is the kind of model which you can use to basically address this kind of a sequential learning problem. So okay, so here I would also like to introduce. So just like for the words, you can create this kind of an embedding. You can create an embedding for each word. There is something known as Tekken's embedding theorem. Okay, so what Tekken's embedding theorem says is that, for example, uh, if you have 3 time series, okay, so I think you must have been introduced to the Lorentz equations in your. We'll see if we can get a good match for this. Okay, fine. I think this is okay. So Lawrence was basically trying to create something similar to weather prediction in 1950s and 60s, and he had these 3 very simple equations, which are dx by dt equal to 10 into y minus x, dy by dt and dz by dt. So in these equations, you can see that x, y, and z are your independent variables, and these are differential equations. So you can basically step ahead in time. You can perform integration, and you can know the value of x, y, and z at time t+1, t+2, t+3, so on. And what you would need to do is you would need to start at some point here in the space. So for some x, y, and z, you can start from any x, y, and z, and then start solving these 3 equations. And what you would get is these kind of graphs. So which are in x, y, and z, and so these are basically time series. Okay, and what is plotted here is also popularly known as the butterfly curve. So you can see that your, so what is plotted is x comma y comma t, x comma y comma z at different time steps. So this is a classical example of a multivariate time series problem, wherein you have 3 time series, X, Y, and Z. And what Teken's embedding theorem says is that, let's say you did not know about Y and Z. Okay, so you do not know anything about Y and Z. So you have, let's say you have set up an instrument which is measuring temperature, okay, at a particular location, and you are collecting the data from it. Now you will get a time series information from that instrument. So you will get collect time series data. Now that time series data corresponds to temperature, and temperature at that location is because of a lot of things that are happening there, right? So it might be because of changes in pressure, temperature, precipitation that has happened. So it has encoded lot of information in it. It is multi-dimensional or multi its dimension. It's a high dimensional system which you are trying to capture using an instrument with just you are getting just a single time series. So you can think of this from this Lorentz equations, that you for now forget about the y and z time series. Just think about your x time series. Just think that you only have your x time series. If I give you this x time series and if I ask you to reconstruct the y and z, will you be able to do that? So Teken's embedding theorem says that yes, you can do that. So there are methods to first of all find out something known as the time delay parameter, and second is to find out what is the dimension of this, what is the dimension of this time series. So you would find out the dimension of this time series, and you would also find out the time delay parameter, and then you can embed a time series in an n dimensional space, and you can create at every time step, you can create an n dimensional vector. So you can from Teken's embedding theorem, and which is a representation of the all the dimensions which have led to the formation of this time series, univariate time series. So this kind of application of like, or this kind of method of creating embedding is not just limited to the natural language processing problems. You can also embed a simple time series in an n dimensional space and then perform the computations with that. That would improve your accuracy. You can try lots of different things with the with that kind of a pre-processing. Now we were okay, so we were discussing about the type of model that you can use so for this kind of a sequence learning problem. So the most simplest one is known as the recurrent neural network, or RNNs. So why we should not use a standard network for sequence tasks? There are some problems. The problems are that the input and output can be of different length in different examples. So for example, if you build a simple deep neural network, it will have a fixed size of input, it will have a fixed size of output. But in a sequential problem, you can have different size of input. For example, you collected maybe 10 days of data sometime, then your instrument stopped working, and then you start collecting the data later, you have 5 days of data, or even it can continue up to 5 months. So in a standard network, the problem is that it won't be able to adjust to the different lengths of different examples. And so this can be, so you can solve it by padding. You can just pad, you can add zeros, but that's not a good solution. And so also a standard neural network, it doesn't share features or share weights across the different positions of the text or sequence. So basically in a time series, you have patterns, you have temporal patterns. So you need information, or you need to share the weights of your neural network across the times. So you cannot do that with a standard neural network. And so RNNs, or recurrent neural networks, so they don't have the two problems as we have discussed. And for a very simple simple example of a named entity recognition problem, or named entity recognition task, wherein you have an input, you have input x, x1, x2, x3 up to xt. So this is a sequence of input. This is that sentence: Harry Potter and Hermione Granger invented a new spell. And then you have these labels. So for each name, you have the label as 1 or 0. Whether if it's a name, the label is 1, otherwise it is 0. And in this problem, your length of sequence, so tx equal to ty. And however, there can be problems where they are not equal and the RNN architecture will be different. So what we get from here is, so we see that we start with an input a0. So let's say it can be some number, and then these neurons, they are outputting a1. So this is the and it's so this layer, it is taking in a1 and x2, and it is outputting a2. So basically you are having some kind of memory which is then transcending across or transcending through the network. And then you are having an output y, so which is y1. So there are basically three types of weight matrices here. So one is WAX. So all the weights which are connecting the inputs to the network. Okay, so to these layers. So those weights are represented by WAX. Now you have WAA. So these arrows, so which are linking the different layers, so that the weights which are shared amongst them, so they are represented by WAA. And then you have WYA. So you are also outputting these Ys. So you would have the weights here. So from the layer of RNN layer to the output or to the label, so you have WYA. So WAX is its size is number of hidden neurons. So in this case, 4 hidden neurons by the number of inputs. So this is the number of inputs, and so the number of hidden neurons by number of inputs. WAA is its size is number of hidden neurons by number of hidden neurons, because you are going from, so you are it's something which is connecting these two layers. So number of hidden neurons by number of hidden neurons. And WYA is NY, so number of outputs by number of hidden neurons. So you can see that this WAA, this is basically shared in the as these weights are shared amongst the different layers. And so the weight WAA is the shared memory RNN is trying to maintain from the previous layers. And some of the visualization will also show you something like this. So you have a single layer here, and you are inputting xt, outputting yt, and you have a recursive arrow. So basically it is feeding in to itself, and which is slightly harder to interpret, and it's easier to roll these drawings into an unrolled version. And for understanding purposes, it's easier to understand from this kind of unrolled architecture visualization. Now, in this discussed RNN architecture, the current output YT depends on the previous input and activation. So this one, it depends on the previous activation. So Y2 depends on A1 and X2. So that's what they are saying. It depends upon previous input and activation. And if you have an example, for example, he said Teddy Roosevelt was a great president. So you are having this as an input. This is a sequence. Now in this sequence, Teddy is the name of a person, but we know that from the word president that came after Teddy. So this word president is representing Teddy. Okay, so Teddy Roosevelt. So the word president is used for Teddy Roosevelt, and not for he. Okay, so it's easy to build a model, or the model can confuse, right? You're building a computational machine which can mistake which can do a mistake such a way that it can identify. So if you ask who is the president, okay, so it can answer you he is the president. Okay, the person who said, who is speaking, he is the president. But actually Teddy Roosevelt is the president. So we know that from the word president that came after Teddy, and not from he and said that were before it. So there is some kind of there is some kind of limitation in the RNN. So for that we will discuss bi-directional RNN. So which also take in the input from the words which come afterwards. So with the from the sequence which comes later. So those are bi-directional RNNs. And now we will discuss how you would perform computations in this kind of an RNN architecture. So for example, you start with some activation A0, and you have these inputs x1 to x of tx. So tx is the length of the input series, ty is the length of output series. So you would first create this activation A, which is created from which is a function, non-linear function g, which can be tan h, relu, sigmoid. You can do anything. And then it's a, so you multiply WAA. So for example, you multiply this A0 with WAA, so, and plus WAX into x plus b is your the bias term. And then to create y1, you would have wya into a1. So a1 you created from here, plus by. So that's how you would create your y1 term. So these are the generalized implement equations of at and yt in an RNN. So the activation function of A is usually tan h or relu, and for Y depends on the task you are choosing. So some activation functions like sigmoid, you can also have sigmoid or softmax. And in a named entity recognition task, we would have two classes, so 0 and 1. Now, in order to help us develop complex RNN architecture, the last equation just needs to be simplified. So the simplified RNN notation. So you can see it is so these are the, yeah. So that's these are the same things. They must the same things. And the way so these algorithms. So the way it would learn is also back propagation. So you have the model generated Ys, and you have the ground truth. So the deep learning frameworks will do back propagation automatically for you, but useful to know how they would work. So you would use for example, for this case, since it's a binary classification task, so you can use a cross entropy loss function, so which is minus y log of y hat minus 1 minus log y into log of 1 minus log y hat. So where y hat is the model predicted y, and then you sum over all the examples, so you get the loss function. And so you would first forward propagate and then do the back propagation, compute the loss. So this loss you are computing at each time step, and then you will back propagate the loss. You would compute the gradient of the loss with respect to, so the partial derivative with respect to a particular weight, and then you will update your weights using your gradient descent algorithm. So W equal to W minus alpha into del L by del of W. And so the back propagation here is known as back propagation through time, because we pass the activation A from one sequence element to another. So we do the back propagation in time. And now you can have different types of RNN. So the first is one to one. So you are just from one number you are mapping to just one number. You can have one to many, wherein you are inputting just one number, or and then you are expecting a sequence of numbers or a sentence. So sentence here or words are also numbers for us. You can have many to one. So many to one is so for example, if you're trying to build a sentiment classification algorithm, so you have a review and then you want to see whether it's a negative review or a positive review. You can have a many to many example wherein you are inputting a sequence of inputs and you are expecting a sequence of outputs. And you can also have many to many in this form, like wherein you have this one is a proper encoder, this one is a proper decoder. So in this one you can have like a one-to-one association, but in a many to many form. So yeah, so we have seen these examples, one-to-one and many-to-one. So now what we will do is we will see some. It's 2:45. We will see some hands-on examples. We'll continue to what we were doing in the from the previous class. So we have seen the image classification, so basic classification. Now we skipped this last time, basic text classification. So will do this example today. Okay, so okay, so this tutorial demonstrates the text classification starting from plain text files stored on the disk. You will train a binary classifier to perform sentiment analysis on an IMDb dataset. At the end of the notebook, there is an exercise for you to try in which you will train a multi-class classifier to predict the tag of a programming question on Stack Overflow. So let us first import these libraries, matplotlib and string shutil re. So this is a very important library, re. It's known as regular expressions. Uh, this is a Python library, and you should be aware of it because uh, it makes your life easy. So we can just very quickly see. Uh, we can see a quick tutorial about it. Okay. So regular, yeah. Uh, okay. So we'll see what this regular expressions library does. It's a very extensive library, and first what we'll do is we already have a GPU. Okay, that's good. So we'll print the TensorFlow version. And this notebook trains a sentiment analysis model to classify movie reviews as positive or negative based on the text of the review. And this is an example of binary or two-class classification, which is an important and widely applicable kind of machine learning problem. You will use the large movie review dataset. So we'll see what this dataset is. So this is a dataset for a binary sentiment classification containing substantially more data than the datasets which were prior to this. And they provide a set of 25,000 highly polar movie reviews for training and 25,000 for testing. And there is additional unlabeled dataset for you as well. And raw text and already processed bag of words format are provided. So see README for more information. And this is the paper wherein they have provided this data set for performing sentiment classification. So this contains 50,000 movie reviews from Internet Movie Database, which is IMDb. So from IMDb, they have basically scraped the movie reviews. 50,000 out of which 25,000 are training, 25,000 testing, And the training and test are labeled, meaning they contain equal number of positive and negative reviews. Okay. So they are, you have like both of them, both the training and testing are balanced. And let us download this IMDb dataset. So we will use this get file function from Keras utils. Now you can see that we are doing list directory, this dataset directory where we have downloaded the data. So we have imdb.vocab, train, imdb er.text, test, and readme. So we would list what is there in the train directory. So you have urls negative.txt, then you have this unsub pow.feed unsub negative positive urls unsup, I think n is negative, p is positive. Okay, so then uh, these directories positive and negative, pos and neg, which are these. They contain many text files, each of which is a single movie review. And let us take a look at one of them. So we will. So you can even see them. So these are our text files which contain the movie reviews. So we select one of these. We select one of these. We have the file name is sample file, and we open this and read this file and see what is there in the data. So Rachel Griffiths writes and directs this award-winning short film, heartwarming story about coping with grief and cherishing memory. So this is the content of the file. So now we will load the data. So you will load the data off disk and prepare it into a format suitable for training. So to do so, you will use the helpful text data set from directory utility. So which expects a directory structure as follows. So you can see that it is defined in the uh, Keras utility, and it generates a tf.data dataset. So with a tf.data dataset, we can basically perform we can perform or we can do training of our models in a very easy form. So it expects that your directory structure is so you are having a main directory and you're having a class A, and then these are your text files, A underscore text 1, A underscore text 2 .txt, and then you have a class B, and then you have these. So class A, class B, for example, are our positive and negative reviews. So then to prepare a dataset for binary classification, you need two folders corresponding to class A and class B. These will be positive and negative movie reviews, which can be found in train POS and train NEG. As the IMDb dataset contains additional folders, you will need to remove them for using this utility. So next, you will see how to use the text dataset from directory utility. So you see we removed this unsub from this directory. So this unsub directory has been removed. So we just have the NEG and POS directories remaining. As in directories, there are other files as well, but as in there are only two directories. So next you will use text dataset from directory utility to create a labeled tf.data dataset. Tf.data is a powerful collection of tools working with data. For working with data, we have already seen that. And when running a machine learning experiment, it is best practice to divide your dataset into 3 splits: train, validation, and testing. So you can see more details on that at developers.google.com, machine learning glossary. So they give uh, and the IMDb dataset has already been divided into train and test, but it lacks a validation set. So let's create a validation set using 80-20 split of the training data using validation split argument. So your batch size that you're keeping is 32. We are we are saying that the seed is 42 so that the results are reproducible. And so the text data from directory utility we are using, and we are passing this as the directory. So in this directory, there are two other directories, POS and NEG, and have to give the batch size, validation split, subset. Okay, so what is it? What is this for? Whether this is for training or testing, and because while testing there won't be any update in the weights, and what is the seed. So let us run this. Yeah, so it says found 25,000 files belonging to two classes using 20,000 files for training. So 5,000 files for the validation and 20,000 for training. So as you can see above, there are 25,000 examples in the training folder, which you will use 80% for training. As you will see in the moment, you can train a model by just passing the dataset directly to model.fit. If you are new to tf.data, you can also iterate over the dataset, print out some examples. So for example, now you have this training data. So for text batch, comma label batch in raw train ts.take. So you just take one batch. So this we have already seen. So one batch is 32 files or 32 reviews in this case. So you will just take one batch and you will just print 3 reviews. So you will print. So you'll say, okay, so this is the review text batch dot numpy I. So from this text batch, so this is Pandemonium is a horror movie, and then you say label. Okay, so this is your review. This entire thing is the review, and this is our label 0. So for one of them, it has created as label 0. So POS I think is label 0, and NEG is label 1. So yeah, POS is level 0. So you can see David Mamet is a very interesting and very unequal director. His first movie, Game of House of Games, was the one I like best. So this looks like a positive review. Let's see this one. Great documentary about lives of firefighters during the worst terrorist attack of all times. That reason alone is why this should be a must collector's item. What shocked me was not only the attacks, but the high fat diet and physical appearance of some of these firefighters. I think a lot of doctors agree with me in the physical shape they were in. Some of the firefighters would not have made it to the 75th, 9th floor carrying over 60 pounds of care. Having said that, I now have a greater respect for firefighters. Realize becoming firefighter is a life altering job. Okay. Yeah, so looks like positive, but I think, yeah, so 0 and 1, I think their labeling also, I mean, that's the labeling is a manual labeling. So people are made to read this kind of reviews and made to label them. So notice that the reviews contain raw text and occasional HTML tags. So you can see that it contains the HTML tags, and you will show how to handle these in the following section. So label 1, what does it corresponds to? Oh, label 1 is positive and label 0 is negative. Okay. So these are negative reviews and this is a positive review. And So these you are taking from raw train. So you are saying raw train ds dot class names 0 and dot class names 1. Next, you will create a validation and test dataset. So you will use the remaining 5,000 reviews for from the training set for validation. And when you're using the validation split and subset arguments, make sure to either specify a random seed or pass shuffle equal to false so that validation and training splits have no overlap. So we said, okay, so we'll say validations. So we pass the training data set here, and we also say the validation split is 0.2. And we have to say that, okay, so this is the validation data set. So it will create this as a validation. And then we have the test directory. So that whole data, entire data is the test data set. So this creates this raw test ts as a tf.data data set, which can be then which we will use for testing. And so you will prepare the data set for training now. You will standardize, tokenize, and vectorize the data using the helpful tf.keras.layers text vectorization layer. So standardization means basically it's like another word for normalization. Tokenize, basically you will select the tokens, or what people would do is they would remove words such as and. So you would basically create or remove those kind of redundant words, and then vectorize the data. So each word corresponds to a vector. And standardization refers to pre-processing the text, typically to remove punctuation. So you would remove the punctuation or HTML elements, simplify the dataset. Tokenization, yeah, you would split the strings into tokens. So that is a single long string. You would break it into tokens and into individual words or splitting on white space. Vectorization refers to converting the tokens into numbers so that they can be fed to the neural network. So as you see above, reviews contain various HTML tags. These tags will not be removed by default standardizer in the text vectorization layer. So you will write a custom standardization function to remove HTML. Okay. So also we have to note that to prevent train test skew means the also known as training or serving skew. So there should be no skew in your data set. Let's see what by that. Okay, so training serving skew is a difference between performance during training and performance during serving. This skew is so basically the model performance at the train and the test time, and discrepancy between how you handle the data in the training and serving pipelines. So that can cause an error. Change in data between when you train and when you serve, feedback loop between your model and your algorithm. So basically they're talking about the difference in the train time, and the serving is basically at the time of deployment. So the kind of if your performance is different, so that is training and serving skew or train test skew. And it is important to pre-process the data identically at the train and test time. So that is very important. Like you should note that for any kind of machine learning problem. And to facilitate this, the text vectorization layer can be included directly inside your model as shown in this tutorial. So this is our customized standardization. So you first take your input data is something which is coming as an argument inside your function custom standardization. You convert entire data into lowercase. So you say tf.strings.lower input data. Script HTML. So you say tf.strings.regex replace in this lowercase data. You replace all these HTML tags with these white spaces, and then what you return is tf.strings.regex replace stripped HTML. So this is your stripped HTML. So you also remove the punctuations. So all the punctuations have now been removed HTML has been tags have been removed. All the uh, text has been made into lowercase. Now you will create a text vectorization layer. So you will use this layer to standardize, tokenize, and vectorize your data. So you set the output mode to int to create unique integer indices for each token. And you also note that you are using the default split function. So we will split the data into different tokens. So one string, that line Harry Potter, and uh, so the Harry Potter. So these will be individual tokens. So you will also define some constants for the model, like an explicit maximum sequence length. So what should be the maximum length of a sequence, which will cause the layer to pad or truncate the sequences to exactly sequence length value. So maximum number of features, so we say is 10,000, and sequence length is 250. So what are features in this case? For example, if we have a multivariate time series data as an input and a univariate time series data as a target, so we have to define the number of, so we can have, like for example, ENSO and IOD time series as input, and we can have the monsoon time series as a target. So those are the features, those are our features. So we have uh, set the max features to 10,000, sequence length to 250, and our so we have this vectorization layer here. So layers.text vectorization, and so we will use this custom standardization function. And so we also pass this max number of max tokens. What should be our max tokens, what should be our output mode, and what should be our output sequence length. So we create this vectorized layer, and now you will call adapt to fit to the state of the pre-processing layer to the data set. So this will cause the model to build an index of strings to the integers. So we'll see this. Wanted to note that only to use your training data while calling adapt. Okay. So what is our train text? So which is raw train ds. So if you remember, we created this raw train ds from here. So raw train ds dot map function will map. So you will pass a function here, and so this will basically map so x comma y to x. Yeah. So this will, what is our x function? Uh, we need to, okay, we'll see this. And then yeah, this one I think we need to check whether this is right or we are missing something here. So you will adapt your training data to the, so you will run this train text data through this vectorized layer. So you will say vectorized layer dot adapt, and then this train text. Okay. Hmm. So then let's create a function to see the result of using this layer to pre-process some data. And you basically, what you would do is you will use this vectorized layer, so over the text, and the label is as it is. So and then you will take batch of 32. You will let's see some examples. So this is our review, which is a TF tensor. The label is negative, and the vectorized review is this one. So vectorized review comma vectorized, so this is first review comma first label. So that we are taking from text batch, which is extracted from raw train ds. So that is, so your first review and first label, they are this entire array. Okay. So you can see that each token has been replaced by an integer. So you can see here, okay, so the shape of this is equal to, I think, 250, and so each string has been replaced, each token has been replaced by an integer, and you can look up the token that each integer corresponds to by calling the get vocabulary. So for example, what does 1287 correspond to? It is silent. 313 corresponds to night, and here the vocabulary size is 10,000. So for example, this 86, if we see 86 is great. So you can see we have great, which is now 86 here. And so now you are ready almost to train your model. As a final pre-processing step, you will apply the text vectorization layer you created earlier to train, validation and test set. So we'll apply these vectorized text to train, validation and test, and configure the dataset for performance. So we discussed this last time also. There are two methods which you should use when loading the model so that IO does not become blocking. And so the first is this cache function, which basically keeps the data in memory after it's loaded off disk, and this will ensure that the data set does not become a bottleneck while training a model. If your dataset is too large to fit into memory, you can use this method to create a performant on disk cache, which is more efficient to read than many small files, and dot prefetch, which overlaps the data preprocessing and model execution while training. So you can learn more about these methods. Yeah, you can go here and learn. So we will run this cache and prefetch functions on train, validation and test data set, and we'll create an embedding dimension. So we will say that our embedding dimension is 16. So we will embed our inputs to or the words into an embedding dimension of 16. So layers dot embedding max features comma 1 comma embedding dimensions. You have a dropout layer, you have a global average pooling 1D dropout, and you have a dense layer. So this is the model. So the layers, the first layer is embedding layer. This layer takes in the integer encoded reviews and looks up an embedding vector for each word index. So these words are learned as the model trains. Now these vectors, the vectors add a dimension to the output array, and the resulting dimensions are batch, comma, sequence, comma, embedding. So you are basically creating for each word you are creating a vector which has the size embedding. So, and there is something known as word embeddings that we will see in the next class. uh, then we are, so how basically you would create from a word, you would create a vector. So that is a whole idea of or concept of word embeddings. And next, a global average pooling layer returns a fixed length output vector for each example by averaging over the sequence dimension. Now this allows the model to handle the input of variable length in the simplest way possible. So then you have dense layer, and the last is a single output node. So which is, so because we want just a binary, we are trying to build a binary classifier which will tell us whether the review is a positive or negative. So then we'll compile the model. So we'll have binary cross entropy from logits equal to true. So we can have just 0 and, so in this case we just have 0 and 1. And the optimizer is Adam optimizer, and the metric that we are additionally following is the binary accuracy. Now you can very simply train the model. You can just say model.fit train ds validation data equal to val ds and epochs equal to epochs. So after this, yeah, you can evaluate the model on test data set, and let us see how much time this takes. Okay, so then you can print the accuracy on your test data set. So it is somewhere around 87.31, and you can create a plot of loss over time. So this is your training loss. The dotted terms are your training loss. The line is your validation loss, and this is your accuracy. So then you can export the model, and if you want to make your model capable of for processing raw strings, you can include the text vectorization layer inside your model. So I mean, so that you can just directly input the text data to your model. So you can you are exporting this model, you are adding, so you are using this sequential to stack vectorized layer and the model, and the last one is sigmoid activation, and then you compile this as binary cross entropy, and also would evaluate this on the test data set. We can see with some examples. So the movie was great. It shows 0.62. Movie was okay, 0.44. So this is just in terms of probability. The movie was terrible, it's 0.36. The movie was worse, 0.29. So yeah, that's all about this example. We were skipping since last classes. So we saw this. So you can, if you are building, you can basically combine the the problems from so natural language processing to our climate or weather sciences, and can do lots of different things. Just scan the papers, try to find out new hypotheses, all sorts of stuff which people have not even tried yet. So that was the purpose of basically discussing this whole subject of sequence models and NLP. We will continue in the next class. Thank you so much for listening.